On the morning of May 18, 1980, a magnitude 5.1 earthquake shook a bulge loose from the north flank of a mountain in Washington state. What followed in the next few seconds was the largest landslide ever recorded on Earth, and an explosion that flattened 230 square miles of forest, stripped 1,300 feet off the mountain's summit, and killed 57 people. One of them was a USGS scientist 6 miles away, a distance everyone believed was safe. That mountain is Mount St. Helens. Since February of 2024, around 350 small earthquakes have rattled directly beneath it. At the same time, the instruments bolted to its surface show the ground quietly sinking rather than rising. On paper, that combination looks alarming. In reality, the data tells a story that is almost the exact opposite of what most people assume it means. And understanding that difference is the only way to judge every future headline about this mountain accurately, rather than just reacting to the word volcano. To understand why this swarm matters at all, you have to follow the plumbing straight down. Mount St. Helens is not a simple pool of lava sitting under a lid. It sits at the top of a system reaching roughly 10 miles into the crust. Near the base of that system, magma forms and climbs slowly upward, eventually collecting inside a storage reservoir several miles beneath the surface. That reservoir functions as the mountain's engine room, and almost everything about recent activity traces back to it. When that underground system takes in fresh magma, when it recharges, the reservoir presses outward against surrounding rock, forcing fluid through existing cracks and putting stress on the crust. Stressed, cracking rock does exactly one thing in response. It produces small earthquakes. Scientists call this pattern a recharge swarm. The name tells you exactly what it is. Not the sound of magma breaking free toward the surface, but the sound of a reservoir slowly refilling miles underground, gently pushing against the rock that contains it. According to USGS research seismologist Weston Thelen at the Cascades Volcano Observatory, what happened in 2024 was precisely this: pieces of magma entering the crustal magma chamber and creating a change in pressure. The earthquakes were a symptom of the mountain feeding itself, not a symptom of the mountain erupting. It genuinely helps to understand just how small these quakes actually were. The magnitude scale is not a simple ruler. It behaves more like a set of stairs where each full step down represents a massive drop in actual energy released. A magnitude 1 earthquake is not a slightly weaker version of something you'd feel. It is thousands of times fainter, the kind of event that only exists as a small squiggle on an extremely sensitive instrument. The 2024 swarm stayed 95% below magnitude 1, meaning someone standing directly above these quakes on the mountain would never have noticed a thing beneath their feet. That is the actual scale. Dozens or hundreds of faint whispers rising from a reservoir far below, not a single loud shout from magma pushing up near the top. That distinction matters more than the raw earthquake count ever could, because 100 whispers from 3 miles down means something entirely different from a single sharp crack a few hundred feet under the crater. There's a detail worth untangling about why independent observers often report far higher earthquake counts than official agency catalogs show, because this gap is the source of a persistent and understandable frustration. For an earthquake to be formally located and entered into the official catalog, the same signal has to register across multiple monitoring stations and be pinned down to a specific point within a tight margin of error. A micro-event too faint to register cleanly at more than one station simply cannot be located with confidence. A seismograph records everything that shakes the ground around it, not just earthquakes. Near a mountain like this, that includes wind-bending trees, a river, tumbling boulders, cracking ice, and the faint arrival of large earthquakes from the opposite side of the planet. Buried somewhere inside that constant background noise are the genuine micro-earthquakes. The official catalog is deliberately conservative. It would rather miss a real signal than falsely invent one that wasn't there. During a similar swarm in the past, the seismic network monitoring this exact mountain stated openly on the record that many more small events were happening than could be formally located. The catalog was never a hidden ceiling meant to conceal the full picture. It functions as an honest floor that openly admits it only counts what can be confidently confirmed. If the 2024 swarm felt unprecedented, it's worth knowing that Mount St. Helens did almost exactly this back in 2016, and absolutely nothing followed. Starting that spring, the mountain produced a swarm of small earthquakes running for roughly 8 weeks, with the network locating well over 100 of them at depths between roughly 2 and 7 kilometers, noting explicitly that many more events were too faint to formally locate. The magnitudes stayed tiny, mostly half a point or below, with the largest only reaching about magnitude 1.3. The rate climbed to close to 40 located earthquakes a week, alarming on paper until you notice what accompanied it, which was nothing at all. No unusual gas readings, no ground swelling, no shallow earthquakes creeping toward the surface. The Geological Survey reviewed that swarm and stated flatly there were no signs of an imminent eruption. The mountain was recharging, the reservoir slowly refilling exactly as it had before, a process that can continue for years without ever producing an eruption. This brings us to the sinking surface, the one detail that both the 2016 episode and the 2024 activity shared, and the one thing that looks strangest on paper. The paradox stated plainly, the reservoir deep beneath the mountain appears to be actively refilling, and yet the surface directly above it keeps going down instead of up. A refilling tank should logically push the ground upward. Instead, instruments have shown years of steady subsidence, the surface gradually settling downward. This is precisely what convinces people something is being hidden, because it seems to violate basic common sense. It does not. The resolution is the single most important idea in understanding this mountain's current behavior. The system underneath Mount St. Helens effectively operates on two separate levels, and critically, they are not locked together. Far below, miles down, the reservoir can be actively repressurizing, taking on fresh magma and charging up like a battery. Scientists documented exactly this dynamic at Mount St. Helens after its last eruption ended in 2008, with monitoring showing the underground magmatic system steadily reinflating from around January of that year onward, even while the volcano itself sat completely silent at the surface. Now consider the shallow half, closer to the top. The young lava dome the mountain built during its last eruption from 2004 to 2008 has been doing exactly what freshly formed volcanic rock naturally does. It cools, crystallizes, releases trapped gas, and slowly contracts under its own weight. During the later stages of that eruption, a receiver sitting on the active lava spine measured it sinking at about 2 centimeters a day. These shallow processes pull the surface downward completely independently of what the deep reservoir is doing. Put both halves together, and you get a volcano quietly charging far below while its shallow skin cools and sags above it. Surface sinking does not mean magma is leaving the system. It means the top layer is cooling while the bottom quietly fills, which is precisely why this mountain keeps catching people off guard. In September of 2025, large plumes spotted rising off the peak triggered a fresh wave of public concern. Those plumes turned out to be 45-year-old ash left over from the original 1980 eruption, lifted off the mountain's flanks by unusually strong wind. The Cascades Volcano Observatory confirmed it. The alert level remained at normal. Not an eruption, just a ghost of one. To understand why the contrast with today's activity matters so much, you have to look directly at 1980 because that is the actual yardstick. The reawakening began in March of 1980 after 123 years of dormancy, with earthquakes and sudden bursts of steam. Then came something with no real equal in the modern geological record. The entire north flank began physically deforming outward, not settling, not sinking, but visibly bulging as magma forced its way sideways into the flank at a rate of roughly 5 feet a day. Over that spring, the bulge pushed outward by something close to 450 feet. That is visible, accelerating shallow deformation, exactly the textbook warning sign today's mountain is pointedly not displaying. Every signal stacked and intensified over those roughly 2 months. The earthquakes climbed steadily upward toward the surface. Steam explosions grew more frequent. The bulge swelled visibly day after day until the rock was deforming faster than it could hold together. Then at 32 minutes past 8 on the morning of May 18th, a magnitude 5.1 earthquake shook that overloaded bulge loose. The entire north flank collapsed at once, producing the largest landslide ever recorded on Earth. With a massive section of the mountain suddenly gone, the pressurized system trapped inside was instantly uncorked. It blasted sideways, flattening forest across roughly 230 square miles, stripping away the upper 1,300 feet of the mountain and dropping its summit from 9,637 feet down to 8,363. Ash reached Idaho by noon. 57 people died, among them USGS scientist David Johnston, monitoring from an observation post roughly 6 miles away, a distance everyone believed was safe. His final 3-word radio transmission became the defining human moment of the disaster. The observatory that watches this mountain today carries his name. Set the two pictures side by side, because this comparison is the whole argument in one place. In 1980, the surface was bulging outward at roughly 5 feet a day. Today, it is quietly sinking. In 1980, earthquakes climbed steadily toward the surface as magma physically forced its way upward. In 2024, tiny earthquakes sat miles down, exactly where a reservoir calmly refills. In 1980, 3 separate signals, inflating, shallowing, and accelerating, all pointed in the same upward direction at once. The 2024 activity was faint, deep, and fundamentally different in every measurable way. Every single element that made the 1980 signature a genuine countdown is currently absent from what this mountain has been doing. Mount St. Helens does not refill itself by accident. Just off the Pacific Northwest coast, a slab of ocean floor called the Juan de Fuca Plate is being forced steadily beneath the North American continent at the Cascadia subduction zone. As that slab grinds downward into the hot interior of the planet, water trapped inside the rock gets squeezed out and driven up into the mantle above. That water lowers the mantle's melting point, and the magma produced rises, breaking through the surface to form the entire Cascade Range, including Rainier, Adams, Hood, Baker, Shasta, and St. Helens, each fed by the same offshore engine. Mount St. Helens is the most active volcano in that entire chain, having erupted more often and more recently than any neighbor, which is why a swarm beneath it becomes national news, while identical activity under a quieter peak barely registers. Scientists are not guessing about what a real reawakening would look like. They already know the specific tells, because this exact mountain has shown them before. A genuine countdown would announce itself through a specific cluster of changes. First, a clear migration of earthquakes gradually shifting from deep down toward the surface, tracing the physical path of magma on the move. Second, a distinct change in the character of the shaking itself, the emergence of a harmonic or volcanic tremor, a continuous vibration signaling fluid and gas actively moving through the plumbing rather than simple rock cracking. Third, the surface flipping from sinking to rising, with measurable inflation replacing ongoing deflation as pressure reaches the shallow system below the crater. Fourth, a noticeable rise in volcanic gases, particularly carbon dioxide and sulfur dioxide, climbing as magma approaches the surface. And fifth, actual steam explosions, the mountain clearing its throat with bursts of superheated water, exactly as it did repeatedly in the weeks before 1980. Not one single item on that list is currently happening at Mount St. Helens. This also happens to be one of the most heavily instrumented volcanoes on the entire planet, wired with seismometers, satellite radar capable of measuring ground movement down to the millimeter, dedicated gas sensors, and precision geodetic receivers, all feeding directly into an observatory built specifically because of what happened here in 1980. Any shift from quiet recharge toward a real reawakening would not slip past unnoticed. The warning signals would show up one after another in instruments purpose-built to catch exactly them. The reason today reads as routine is not because anyone is looking the other way. It is because the people watching hardest, using the best monitoring tools ever pointed at this specific mountain, currently see a volcano refilling, not a volcano actively rising toward eruption. There's also a specific reason this particular mountain, rather than one of its taller neighbors, keeps generating headlines even during quiet periods. The magma Mount St. Helens produces is a thick, high silica type of rock called dacite. Thick magma is genuinely dangerous magma. It does not flow easily, it traps gas internally, builds up pressure over time, and when it finally does fail, it tends to fail explosively rather than pouring out gently like a slow river, the way Hawaiian lavas do. This is the fundamental reason the 1980 eruption was so devastating and so dramatically different from a typical effusive eruption. The trapped gas pressure built up until a catastrophic release became the only possible outcome. Mount St. Helens is also unusually young and geologically active, a mountain that has rebuilt and torn itself apart repeatedly throughout its history. That specific combination, a genuinely busy volcano fed by sticky, gas-heavy magma, is exactly why even a small swarm beneath it draws intense attention that an identical swarm under a quieter peak simply never would. The stakes here are objectively higher, which is why so many eyes stay locked on this one mountain in particular. It's also worth appreciating just how much the science of monitoring this mountain has improved since 1980. David Johnston died at a distance everyone considered safe precisely because nobody in 1980 fully understood the mechanism of a lateral blast caused by flank collapse. That gap in understanding drove an enormous investment in monitoring technology and eruptive modeling across the following 4 decades. Today, the network watching Mount St. Helens includes seismometers sensitive enough to locate magnitude 0 events, GPS receivers that can detect ground movement at the millimeter scale, satellite radar systems that produce detailed surface deformation maps from orbit, and continuous gas monitoring instruments positioned around the crater. This instrumentation is part of what makes scientists confident in reading a quiet recharge signal as routine rather than alarming. They are not making an educated guess based on limited data the way geologists in 1980 were forced to. They are reading from an exceptionally dense, purpose-built monitoring system that was specifically designed around the lessons of what this mountain did and how little warning it gave the first time. Mount St. Helens is alive, quietly refilling, sitting at normal alert status. There are a few concrete things worth actually tracking in the coming months, the same things the observatory itself will be watching closely. First is whether the swarm's rate, which quieted significantly since its 2024 peak, stays low or begins climbing again toward the elevated levels seen that spring. Second is the ground itself, whether the ongoing deflation continues as expected, flattens out entirely, or the one shift that would genuinely change the picture reverses into measurable inflation. Third is the specific depth of any new earthquake clusters, since a migration toward shallower depths would be a far more significant signal than an increase in raw count alone. And fourth is simply whether the Cascades Volcano Observatory issues any new formal statements about this activity, since they have been consistently transparent about what they're seeing, the word recharge appearing openly in their communications, rather than being something anyone had to dig out of suppressed records. Until one of those specific signals actually changes, the honest read stays remarkably steady. That looks so alarming at first glance is simply the top layer cooling while the bottom quietly fills back up. This mountain is not counting down toward anything. It is performing routine maintenance, the slow underground work of a volcano operating between eruptions, on a schedule measured in decades rather than days. When the real countdown eventually starts, it will not look anything like this current quiet pattern. It will look like 1980, loud, shallow, and rising fast. Understanding that difference now, while everything stays quiet, is exactly what will keep you from mistaking the next false alarm for the real thing. If breaking down the science behind these stories is useful to you, a like and a subscribe genuinely helps this channel keep making it. Thank you for watching, and I'll see you in the next one.